So let's start today's lecture, kernel methods. I hope this will be like the last lecture for this kernel methods. So just a quick revision. Am I audible to you guys?
Yes, sir.
Yes, sir.
Fine. So quick revision is like we were trying to see what are kernel methods and how to use them. So before that, we have talked about like there are two approaches to train the model and then do prediction. One approach is we learn the parameters and then throw away the data. And using those parameters, because we learn a model, then we use the model to predict. The second approach is that uh, for linear parametric model, we convert our things for in dual representation, and in dual representation, we can predict there as well. But here we use data set at the time of prediction. And for parametric models, when we convert it into a dual representation, these parametric models, linear models, I would say specifically linear parametric models, when we convert them into a dual representation, then we see that our data samples appear into the inner product form or scalar product form, which is also known as like dot product. That is like phi transpose phi. So we say that phi transpose phi can be represented as a kernel function, right? So this is what we have said. Then just to show, just to prove our point, we just took that linear model, which is regression, and we have shown that this dual representation is actually using this matrix, and this K matrix is nothing but it's every entry is a dot product here. This is what we have learned. Then we found out during the prediction also that prediction at the time of prediction also we are actually taking the x where we want to predict and then take a dot product with every sample in a data set that will give this vector k, and then find it out just to weight this target variables with this k vector using this matrix, right? So intuitively we have discussed this as well. So then we said that like how to construct the kernel functions, right? How to construct the kernel. So one is very simple, that we have linear kernel where we just show that in the feature space or in the projected space we can take the dot product, right? So phi is nothing but the space where we have just applied a basis function and we are now in some m dimensional space. So we are taking a dot product there, right? So this is how like this is a very naive way to calculate the kernel function, right? You are in a real space, you project your x using phi function into the other space where you have high dimensional vector. You take your those second vector, apply again the phi function over it, and you get the second projected vector. And then in this projected space, you take the dot product. By doing this way, we see that the computational cost is very high. If you are projecting in 1 million, the dimension of the space is 1 million, right? So then the number of addition and multiplication will be 1 million. So the alternative approach to kernel function is like, can we use this some trick so that we get the same result what we have here? We get the same result what we have here, but the computation cost should be constant, not in the terms of m, where m is the dimensionality of the projected space, right? So just to prove that point, we have said that, okay, take this example, right? So here you have this x transpose z. So x is a two-dimensional vector, z is a two-dimensional vector. You project them into three-dimensional space using some phi function, right? So then in three-dimensional space, you have this longer vectors here, 3 by 1, 3 by 1. right? You take a dot product. When you take a dot product, there will be three multiplication and some two additions. So five, you will take five, you will do five operations here, right? And the other way is, this is one way to do this. The other way is you do the dot product here itself in the real space, right? And then whatever you get, you will get a scalar number. You square that scalar number here, and eventually the value which you get from here, right? The same value you will get from there also, right? But the computation what we have done here is like two multiplication, one addition. So three operations plus one square. The plus five, we have done four operations here, three plus one. And here we have done five operations, right? But this is insignificant in terms of like when we have low dimensional. If you see, if you project into m dimensional space, right, then the number of operations in m dimensional space will be m multiplication plus m minus 1 addition, right, plus m minus 1 addition. So it will be 2m minus 1 operations for a dot product in m dimensional space. And this will remain same here. This will be 3 4 only, right? So then you see that you will get the same value using your kernel function itself, right? So this is what we have discussed, right? So the kind of projection we get from this kernel function or kernel trick, right? This is a kernel trick, right? Rather than projecting actually, we are producing the same effect by doing this kernel trick. The space that we get, the projected space we'll get is like in terms of this kind. First component will be get squared. Second quadratic term will be square root 2x1 x2, right? And third term will also be quadratic, that is x2 square. Right? This is a kind of a projected space you will get, or feature space you will get using this basis function, right? It is a three-dimensional space, but you can see that this whole space will not be get covered because you have some constraints here, right? And there are some specific forms, so it will be a subspace in three dimension. So it will be a subspace in this three dimension, maybe some plane kind of thing, right? So, but yeah, eventually we will see like this will work. So if you want to generalize it, because here you see that we have only quadratic terms, we don't have those monomial terms and constant. The other trick is you just need to modify your kernel function, right? So we'll see it, right? So the gram matrix K should be positive semi-definite for all positive choices of the set Xn. So the thing that you need to remember here is that there are two properties we need in kernel functions. One, it should be symmetric, right? It doesn't matter like whether you are doing the K kernel function. If you, there are two parameters we are feeding here in this kernel function. The order will not matter. It is symmetric, right? So K of xy will be y of x, right? The other thing is it should be positive definite number. It means the gram matrix, if you take K and you multiply it with any vector x transpose on left and x on right, you always get some number greater than or equal to 0, right? This is what is required for a kernel function. The naive reason, not very theoretical, I am here giving here is that when we project it, it will be some Hilbert space, right? So in short, you say that it will be some m dimensional space. So not to very confused about the things. So we will be projecting into R in some m dimensional space because of this kernel function, right? In that kernel function, we need to calculate the norm of a vector, right? So norm of the vector will be calculated when you do x transpose x. That will be the length of the vector, and when you take a square root of it. If your kernel function is not positive definite and it can produce a value that can be less than 0, then the length of the projected vector can also be negative, right? Which is violating the Hilbert space property. So those who want to take this by this argument, they can keep it in their head, otherwise they can ignore it completely. It will not affect your understanding from here onwards, right? Though it is on the record, it is on in the recording, you can hear it as many times as you can. So the thing is that it will just to the vague or like some reason which you can find it out why k should be positive definite is this one, right? So there are two properties. It should be symmetric, and your k matrix should be positive definitive semi-definite matrix. So if in two dimension, I don't know like whether you have an idea about positive semi-definite matrix or not. Can you tell me anybody who knows positive definite matrix? What is the property of positive definite matrices? Have you ever heard about positive definite matrices? In linear algebra, you must have done that,
Yes,
right?
sir.
Okay, what is a positive definite matrix? Yes, Ashutosh. What is positive definite matrix? Anybody in the class wants to say something about positive definite? Yeah, all eigenvalues are positive. Very good. So what it says to you. So intuitively, if you see that if you have some matrix, some P, right? So if you just, let's say it's a 2 by 2 matrix, right? If it is 2 by 2 matrix, you multiply some vector on here, x transpose on right, on left, and x on right. So you will get some form, right? Which is kind of a quadratic form where the coefficients will be given by this p, right? So it is a scalar number, right? It is always a scalar number. This product will be a scalar number. And this form is a quadratic kind of a form here because it is x transpose on left and x on right. So this scalar number should always be positive. If you want to plot it for every x, let's say this is a two-dimensional plane. This is a two-dimensional plane, right? So this is x1, this is x2, and I'm saying for every x it should be positive. So whether you take this point in this plane, whether this take this point, so they're all vectors, right? So for every vector you feed into this function, which is the what is the function? You feed this into this function x transpose px. You will get some scalar number which is positive. So it will you will see this kind of a structure here, some bowl kind of a structure, where for zero value you will get zero, and the rest of x will always give you some positive number, right? So it may be this kind of structure you will see here, which is always above the plane of xy, x1, x2, right? And it will be touching somewhere at zero, right? This is what we see. Even this is positive, that's semi-definite. This kind of tub, kind of a structure, right? So it is equal to zero at these many places and greater than zero others inside, right? This is how you can see it. So one powerful technique for constructing new kernel is to build them out of a simple kernel functions, right? So if you know some kernel function, and then you can do some manipulations to form new kernel functions. For an example, if you have k1 kernel function and k2 kernel function, there are two kernel function. Then you take a composition of it and to form a new kernel function. So c is a constant here. You multiply it with some kernel function, you will get new kernel function, right? Even you take some function on left and some function on right, and you multiply it with some kernel function, you will get a valid kernel function. What is valid kernel function? It has two properties, symmetry and positive semi-definite, right? So you can do all these things. You can do all these things and you will always get the valid kernel, right? So some kernel functions to remember here is, if you do this, you will get, you know this, you remember this time of function, right? X transpose X dash 2. We have just done in previous slide. So there we had seen that only quadratic terms were available. But if you want some constant and monomial terms, you just add C with this X transpose X plus C. Adding this C will give you all those constants plus some linear terms and then quadratic terms, right? You can see it on your own. Here you see all the terms that appear in the vector using this kernel function will be having only m order terms. But if you add C here, you will see all the terms from constant, linear, quadratic, cubic till order m, right? So this is how you can just expand your subspace in that Hilbert space of m dimension. One of the most, if you don't know which kernel function to use, then by default you can apply this Gaussian kernel, right? So this Gaussian kernel can be written like this, right? And generally it's seen as like we are doing a dot product in infinite dimensions, right? So if you project some x and into some infinite dimensions, theoretically it is not, theoretically it is possible, practically it is not possible to project something in infinite dimension, right? Because infinite is something very large which cannot be accommodated by your computation or your computer, right? So it's some infinite dimension x. So if you want to produce the same effect that you have projected your x in some infinite dimension and then take a dot product there, you can use this kernel function which is known as a Gaussian kernel function. It is not actually a distribution because there is no normalizing constant here, right? It is just e to the power and minus x dash square divided by 2. So this is a scaling factor. How broad it is, right? You know, this is a concept of variance in Gaussian normal distribution. So if you just see this part only, which is in the power of exponent, you can expand it like this, right? Because it is e to the power something, so it get multiplied, right? So this is my first term, this is my second term, and this is my third term, right? And it is a multiplication of these three terms, and you know this is a linear, uh, this was a linear Gaussian kernel. I have been telling you since I started teaching you kernel function. If you take an exponent of it, it is still a valid kernel. If you multiply all these valid kernels, you will get a valid kernel. So it is a valid kernel, right? But if somebody asks you that, can you show it like whether it is whether you can project it into infinite dimension, how you will see this as a projection? So you just expand it. So you just expand this exponential series, right? So you see it here like this: exponent x transpose. Rather than x dash, I will write y so that it is easy to see. So it is x transpose y. If you just expand this exponential series, you will get this. There are two. Uh, just a minute. Hold on. So you will get a longer vector, which you can see as like a dot product. Hmm. So how we can write exponent series? Anybody can recall this for me? So it is like this. So we can exponent series can be write like this: exponent of x is equal to summation xk upon k factorial, right? Xk upon k factorial, xk upon k factorial, right? from 0 to infinity, where k is equals to from 0 to infinity, right? So if you write x transpose y, then you see that first term will be nothing. That first term will be 1, right? The second term will be xy. The third term will be xy square, right? Which is nothing but x square y square upon 2 factorial, right? So upon 2 factorial means you can write it root 2 factorial into root 2 factorial, right? Then the third term will be x cube y cube upon root 3 factorial into root 3 factorial, right? And you keep on writing this. So if you write in terms of a dot product, the first vector will be 1 x square upon root 2 factorial x upon root 2 factorial, right? Then it is x cube upon root 3 factorial, root 3 factorial, and likewise, right? So it will keep on going. Similarly, you can write it in terms of dot product, and y will be same expanded as this x. 1 y square upon root 2 factorial. You got my point or not? Can you write yes or no for this? It keep on going like this, and it is still infinity, right, guys? Very good, very nice. So these are the terms like which people can ask you in terms of like interviews. You should be like good at understanding this, and they are very simple to understand intuitively. So now this Gaussian kernel is like projecting something in infinite dimension, and it may sometimes overfit also because you are having very generality. So you are trying to fit in a infinite space, right? So this is like how you can see it. Okay, this is now you equipped with this knowledge. Before proceeding, do you have any question here till here? Anybody? Fine. Okay. So you can be more like responsive in the class. I just get 2-3 responses only. So please try to respond at least so that I am aware that you are like healthy and live and very much interested in learning. Very good. Okay. Let's do for kernel regression. So you have this is a beauty of like you just apply, you have like lot of kernelized version of algorithm we will see in future for PCA also for support vector machines, and just I have shown you here, just I have shown you here that for linear regression also, right? We have just this K for this Gram-Smith matrix. You have this Gram-Smith matrix. Now, rather than putting, can anybody tell me like how to apply a Gaussian kernel for this linear regression? Anybody in the class want to tell how we can apply Gaussian kernel for this linear regression technique? Just I have shown you here in dual representation. Anybody? Are you connected, guys? Like, are you there? Yes or no? Please tell me whether I'm connected or not. Okay, fine. So, what do you think? Like, how you will going to apply this Gaussian kernel technique? Uh, like, you want what you want now? You were doing linear regression rather than using basis functions, polynomial basis function. You thought, okay, what I will do? I just project my x into some infinite dimension, and and then fit my model there, right? Linear model there. So projecting x into infinite dimension, I just shown you that you can use Gaussian kernel there. So now I want you to apply that Gaussian kernel technique for linear regression. How you will do that? So just I told you that this is your this is when you want to fit a where this is how you need to get the value of a, right? And in this a there is a Gram-Smith matrix, right? And lambda will be a kernelized lambda is nothing but like how you want to regularize. Once you get value of a, you are applying in terms in prediction here, and you get this form, right? You get this form. You get this form. So anybody wants to tell me like how to apply Gaussian kernel here? It is very straightforward. So see, so if you want to predict an A, so in A, I have this matrix A, which is written here, and every entry of K will be what? And you can tell me what is every entry of K? What is every entry of K will be? M an entry M comma n entry of this K matrix will be a dot product between okay M. So the dot product of this K will be the every entry of this K will be a dot product. It is like if it is a linear regression, it is like phi transpose xn comma phi xm. Phi xm, right? So I just showed you that every entry can be written in x transpose xm into phi transpose xm into phi xm. Then I told you that rather than doing actual projection, you can apply a kernel technique. So the every entry what you can write in this matrix here will be like this. K entry mn can be written like this. E to the power x n x x m minus x n whole square upon 2 sigma, right? So this is how you can do this every entry, because now this every entry will be taken as that it will be projected into some infinite dimension, and there you have a scalar product. You got this point? Can anybody unmute and so that we can talk a bit? Hello. Hello. Are we connected, guys? Just to check.
Yes, sir.
Okay. So do you understand like in the what I am teaching here? Akash, you understood this thing? So in kernel matrix, Gram matrix, we have this entry, which that entry can be seen as a dot product. But I want to do some, I want to apply some Gaussian kernel. So rather than doing a dot product there, I just apply Gaussian kernel, which is nothing but a dot product in infinite space, right? So each entry in this case will be like the dot product in infinite space, right? So this is how I can apply my kernel here. So I always apply my kernel functions on this k matrix, the gram matrix, right? The moment I want to apply like a polynomial regression, which how I will calculate the entry for this k matrix? I will calculate the entry of this k matrix by using this regression, right? If I want to do a polynomial regression. So this is how I will calculate the entry. So this is like a polynomial regression, and the projected space for this polynomial regression will be m order. The polynomial is of mth order, right? This is how I will do it. Okay, so let's start a new topic here, kernel regression. I want you to just see it very carefully. This is the first time I'm using a giant probability distribution, and which is actually working. Though theoretically we have discussed so many times, but this is the time like we have used it for a regression, right? So let's see what is kernel regression. So before I go diving into the concept, I want you to see this, revise this, recall this concept. If you remember that in posterior distribution, that was a mean and a variance, right? You remember this? Yes or no? We have just done before that. Very good. So this was a mean. So now if I want to predict, so how I was predicting? I was predicting this way, right? So I was predicting in very simple sense. So this is why my mean, which is nothing but it's a posterior of a W, and the mean of that posterior W is M. So I want to predict for some X. So what I do, I W transpose X is my prediction, where I have used W, which is nothing but the mean of the posterior, right? So I have used mean of my posterior. So because it is the most probable W in the posterior. So then when I'm using, so I will write it like this: Mn transpose X. So X is the place where I want to predict, right? In my regression. Even I can write it like this: X transpose Mn, right? And what is Mn? What is Mn? So I just replace this Mn, which is nothing but beta Sn phi transpose T here, right? And this X transpose is as it is. Then we see that, right? This is nothing but it's a design matrix, right? So here there is a column. You remember? This is a transpose of a design matrix. So there are the columns, and this is a target value, target vector. So if I see it, this is my design matrix transpose. So all samples are in column, right? And this is my target variable T. So it means whatever the targets I have, I put it in T1, T2, T3 till Tn, right? And if I see it, this is nothing but it's a linear combination of all these columns. So I multiply this T1 with this first sample, this T2 with second sample, this T3 with third sample, and this T4 with fourth sample, and Tn with nth sample, and then I will sum it. Yes. So yesterday we have discussed it. So this is what we have done. So it is like we have taken a dot, we have taken a product of a nth sample with the nth target value, and then we are summing them up. And these are all the remaining terms which are as it is from this expression, right? So they are come as it is here, right? Then you see, if you see it now, if you see it now, then what you can replace this thing here as your kernel function like this, right? Because what it says, that you are taking a dot product between the X where you want to predict. This is the X where you want to predict. And these are all X's which is in your data set, right? So this is the X where you want to predict. And these are the all X's which is in your data set. You are taking a dot product keeping this matrix in between. So it is kind of an inner product in this transformed space, right? So just assume if S is identity, then it is nothing but a state dot product, right? So because it is a equivalent kernel, so Sn will be defining the my transformed space. So it is a dot product between every sample in a data set and the X where I want to predict, right? Then what it will give me? It will give me the distance, like approximation of a distance, how close my X where I want to predict with each of the sample. And then I multiply, and then I'm weighting it with the target value, right? Then I'm taking a sum of it, right? It is nothing but it's a weighted sum of your target values, and the weight will be decided by the closeness of your predicted X in the data set with each of the sample. So yesterday I have discussed this thing, right? So here this kernel is nothing but it's a weight. It will tell you how your predicted X is far from your samples in a data set, and then you're weighting it with the target value. You sum them up and you will get a prediction, right? So this is the other way to see it. Fine. So here the second term is that if you want to see like how your output is covaried with the other output. For an example, this was a curve. So if you want to take how this y is covaried with this y, like how it changes. So the covariance, if you find it out, then you just y is can be written as x transpose w, and this also can written as x transpose w or w transpose x, the same thing. Then you take a multiplication because they are scalar, then it is phi transpose will come this way as it is, this phi will come as it is, and w transpose it is the outer product of a vector, right? So w transpose is outer product, which will be a matrix, right? So this matrix is like a one rank matrix which is decided by this Sn, and it will tell you like how they much are covariant. So if they are very far, if X is very far, if the X is very far, then actually this Y doesn't correlate. If the X is in very close, then Y is actually correlate, right? This is what it means. Okay. So I hope this is like a different view to see this equivalent kernel, which is derived from directly from the linear regression, right? So linear regression can be seen as like the weighted sum of the target values, and weight will be decided by the closeness of the predicted X with each of the sample in your data set. Fine. Any questions so far still here? No? Okay. So let's do this kernel linear regression for this Nadaraya-Watson model. Before then diving into a concept, I want you to discuss some Poisson density estimator, right? So let's say you are in some space. Very understand this concept very clearly, right? So today I will continue after discussing this concept. For an example, somebody gives you some data set. So this is your data set, right? It is not labeled, right? So these are the points scattered somewhere in the space, right? They are scattered somewhere in the space. Now somebody comes and asks, so this is your data set. Somebody comes and asks you, right? What do you think? What is the density here? So this is your variable X, and you want to calculate the density. What you will do, you just take a square of 1 centimeter each and put this X as a center here, right? Similarly, you do this 1 square centimeter, put X this as a center. Then you do this here, right? You do this here, right? 1 square centimeter, 1 square centimeter, 1 square centimeter, and 1 square centimeter, right? So because I have used 1 square centimeter, so my scope of this window is limited. What I can do, just to make you further understood, assume that you, rather than using these square boxes or windows, you are using some kernel radial basis function, right? What is radial basis function? It is like putting your exponent, right? Putting your exponent where mean you keep your x. So keep this x as a mean here, right? So this is your mean, and then any x where you want to calculate the density. So this x is the this one where you want to calculate the density, right? And it is square. So it is a radial basis function. So it is nothing but it is like a Gaussian distribution, unnormalized Gaussian distribution around this x, right? And for every x you keep as a mean and then do the same thing. So then you will see this way, right? So just for to make it understand, I will only do some small. So this is one. So this is one of my Gaussian, right? So these are the level curves. So this is my second Gaussian, and these are the level curves, right? So if I want to calculate the density at this point, right? And or if I want to calculate the density at this point, what do you think? So this is point 1 and this is point 2. So then calculate the density. I will use simple formula. I will add all the probabilities for each of the Gaussian and then normalize them, right? So what I do, I calculate what is the probability of this point from this Gaussian. Then I will calculate a probability of this point from this Gaussian. So this is P1, P2, right? And then I sum them up, right? Then I will sum them up and I will not divide by 2, right? Similarly, I do this for this also. So then I calculate the probability for this point from this Gaussian, and I will calculate the probability from this Gaussian, sum these probability and divide by 2. What do you think? Which probability is bigger for point 1 or point 2? Right, P2 is greater. So then you can calculate the probability for every point in this space because this is a space, right? So you have a lot of points. So you calculate the probability for every space, right? So you are doing nothing but you are actually calculating the density. So density is a term when we use probability in continuous space, right? So you are calculating a probability for every point in a domain, right? Using this Bayesian window. So it means the two will be very much collecting the probability if it is surrounded by so many points. And if a point is not surrounded by anybody, nobody is in its neighborhood, then it will get very less contribution. It is almost zero. So then you will have a continuous probability estimation over whole space, whether it is zero, whether it is very small, but you will get something. So it will be a smooth density estimation, right? So in unit dimension or univariate. So if this is a data set, so you will get this kind of a density, right? I hope this makes sense to you intuitively. Only two guys. Yeah, very nice. So keep this thing in your head. What is this Gaussian density estimator? I will definitely reuse this term at times of k nearest neighbor, but now because I need to do this kernel linear regression, this things is good enough for you to understand it. So this is a Gaussian density estimator. I can estimate density over whole space using this formula, right? Using this formula where f can be any density estimation, where f can be any window, right? So it can be a square window, or f can be a function which can approximate by radial basis function. So just I have misused the term here that it is a probability. So it is not a normalized exponent, right? So that's why if it is not normalized, I'm using it only as a x radial basis function, radial function, right? Radial function, not even basis function, radial function, right? So so I can use my f, and f will decide the window, right? What kind of window? So this is a discrete window when I take a square, and this is a continuous window because it will cover from minus infinity to plus infinity wherever you go, right? So just to approximate continuous, so because if you estimate a density, so in if you just see in one dimension, so you can find a density like this, which is broken, right? But if you estimate a density using this, you will get a continuous smooth density estimation. So these are the, it depends like what kind of estimation you want. So then really you pick your f based on that. So this will be the concept for your tomorrow's regression. That is Nadaraya-Watson model for kernel linear regression. So if you don't understood this, if you still not have a clear idea, please read this Gaussian density estimator. The things will be same where what I just told you, right? So we'll continue tomorrow. Thank you very much.